Something happened on the night of February 24th, 2026, that every major space agency on the planet quietly took note of, and almost nobody in the general public was told about it. In a single night, one telescope fired off 800,000 cosmic alerts. Not over a week, not over a month. One single night. Scientists sat in front of their screens watching notifications flood in faster than they could process them. Explosions of dying stars, rogue asteroids, black holes waking up in distant galaxies. And here is the part that should stop you cold. This was just the beginning. There's a mountain in Chile. It sits at 2,782 meters above sea level in one of the driest, darkest, most isolated places on Earth. The air up there is so thin and so clean that on a clear night, you can see the galaxy not as a smudge on the horizon, but as a burning river of light stretching from one end of the sky to the other. For decades, scientists dreamed about placing something on that mountain. Not just any telescope, something that had never been built before. Something so powerful, so precise, so incomprehensibly wide-eyed that it could watch the entire southern sky and catch every single thing that moved, blinked, exploded, or disappeared every single night for 10 consecutive years. That dream just became real. And what it has already shown us in its very first months of operation has left the global scientific community in a state that can only be described as stunned silence, followed by barely contained excitement. The Vera C Observatory sits atop Cerro Pachón in Chile, housing an 8.4-meter telescope equipped with the largest digital camera ever built, a 3,200 megapixel instrument roughly the size of a small car but twice as heavy, assembled at SLAC National Accelerator Laboratory, and designed to execute the most ambitious sky survey in the history of astronomy. Think about what 3,200 megapixels actually means. Your phone camera, the one you use to photograph your food or your family, has somewhere between 12 and 50 megapixels. This camera has 3,200. That is the equivalent of 260 modern smartphone sensors fused into a single, perfectly calibrated eye pointed at the cosmos. And this eye never blinks. It never sleeps. It is watching the sky right now as you read this, capturing a new image approximately every 40 seconds. But here is where the story gets strange, because this telescope was not built simply to take pretty pictures of nebulae. It was not built to satisfy curiosity or to produce stunning screensavers. It was built to answer questions that have haunted physics and astronomy for over a century. Questions so fundamental that if we get the answers wrong, or if the answers turn out to be something we never expected, then everything we think we know about the universe, about matter, about time, about reality itself, may need to be rewritten from scratch. Here's a fact that most people outside of astrophysics have never truly confronted. The familiar objects around us, people, planets, stars, entire galaxies, account for only about 5% of what actually exists in the universe. The remaining 95% is something else entirely. Scientists call it dark matter and dark energy. They know it exists because of its gravitational fingerprints, because of the way galaxies spin faster than they should, because of the way light bends around objects that appear to contain nothing. But what dark matter and dark energy actually are, what they are made of, where they come from, why they exist, remains one of the deepest, most embarrassing mysteries in all of modern science. And the Vera Rubin Observatory was engineered from its very foundations to go hunting for them. Every 3 nights, for the next 10 years, this telescope will complete a full scan of the southern hemisphere's sky, generating 60 million gigabytes of data. A living, breathing, ultra-high-definition time-lapse record of the universe. Let that number settle in. 60 million gigabytes. To put it in perspective, if you tried to download all of that data on a standard home internet connection, it would take you approximately 150,000 years. This is not a telescope. This is a time machine, a cosmic surveillance system, a planetary-scale early warning network, and a deep universe research laboratory, all compressed into one instrument sitting on a Chilean mountaintop. Now here is where the story truly begins to accelerate. Because most of the world was told about the telescope's existence, about its construction, about its grand ambitions. And then, quietly, the news cycle moved on. People assumed it was another big science project, impressive, distant, abstract, something for PhD students and peer-reviewed journals. Not something that would shake the foundations of what we know, and not something that would do it this fast. On June 23, 2025, the Rubin Observatory team revealed the telescope's first images to the world at an event in Washington, D.C., with hundreds of watch parties hosted across the globe. Scientists who had spent decades designing this instrument, lobbying for its funding, surviving budget crises and technical setbacks and engineering nightmares, finally saw what it could do. And what they saw was not what they expected. It was better. Enormously, almost incomprehensibly better. In just over 10 hours of test observations, barely one working day of pointing the telescope at the sky, Rubin had already captured millions of galaxies in Milky Way, stars, and thousands of asteroids, not discovered over months, not cataloged over a year, 10 hours. One afternoon and evening of testing, and the telescope had already seen more of the universe than most instruments see in their entire operational lifespan. Think about what that means, because most powerful telescopes are like snipers. They point at one tiny patch of sky, zoom in with extraordinary precision, and stare at that single target for hours or days. That is how the Hubble Space Telescope works. That is how most major observatories operate, and they produce beautiful science. But the Rubin Observatory is something else entirely. No other telescope has been able to detect both real-time changes in the sky and faint or distant objects at the same time on this enormous scale. It is not a sniper. It is a surveillance grid. It sees everything all at once, every night, and it remembers every single frame. The very first images released publicly showcased the telescope's expansive field of view, from glowing nebulas filled with the raw material of new stars, to what appeared to be countless, almost uncountable galaxies, stretching toward the edge of the observable universe. Scientists looking at the data described the experience as overwhelming, not because the images were beautiful, though they were, but because of the sheer volume of information embedded in each one. Every single image from the Rubin Observatory contains within it the light of billions of objects. Objects no human eye has ever seen, objects no instrument has ever recorded, objects that may not even fit neatly into our current categories of what a cosmic object is supposed to be. And then came February 24th, 2026. That is the date that, in the opinion of many astronomers who were watching closely, marks the real beginning of a new era in human understanding of the universe. On that single night, the Vera C. Rubin Observatory issued 800,000 alerts to astronomers around the world, notifications drawing scientific attention to new asteroids, exploding stars known as supernovae, active galactic nuclei, which are glowing supermassive black holes at the centers of distant galaxies, and variable stars whose brightness changes over time. 800,000 alerts in one night, distributed globally. And the truly staggering part is that this number, 800,000, this flood of cosmic notifications that overwhelmed research teams from Chile to California to Europe to Japan, is not the telescope's full speed. It is not even close. The alert system is expected to eventually produce up to 7 million alerts per night. 7 million separate cosmic events detected, classified, and broadcast to scientists around the world, every single night, indefinitely, for 10 years. There is no precedent for this in the history of astronomy. There is no framework, no protocol, no existing infrastructure that was built to handle this kind of data torrent. Scientists are not just discovering new things. They are being forced to fundamentally rethink how discovery itself is supposed to work. These discoveries were made by the Simony Survey Telescope at the observatory and distributed globally within about 2 minutes of detection. 2 minutes. From the moment the telescope's camera registers a change in the sky, a star that was not there yesterday, an asteroid that has shifted position, a galaxy core that has suddenly brightened, to the moment that a scientist on the other side of the planet receives a notification on their computer, 2 minutes elapse. This is astronomy operating in real time. This is the universe being live-streamed, and the implications of what that means for planetary defense alone are enough to keep entire government agencies awake at night. In just a month and a half, during early optimization surveys before the full mission even began, Rubin discovered over 11,000 never-before-seen asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects. Read that again carefully. 33 near-Earth objects. These are rocks, some of them potentially very large rocks, whose orbits bring them relatively close to our planet. Before the Rubin Observatory, we did not know they existed. They were out there, moving through the darkness, completely invisible to every instrument we had pointed at the sky. And now we know about them. The question that logically follows, and it is a question that planetary defense researchers are already actively working on, is how many more are there that we still have not found? If 33 near-Earth objects appeared in 6 weeks of pre-survey scanning, what will 10 years of full-power observation reveal? But the asteroids, as alarming and as scientifically significant as they are not the deepest reason this telescope was built. The real target, the hidden mission at the heart of the Rubin Observatory's decade-long survey, is something far more elusive. Scientists intend to use the observatory's data to figure out how dark matter is, distributed in our galaxy, from the largest cosmological scales down to very small scales, by observing stellar streams, long chains of stars that trace ancient orbital paths and carry within them the gravitational scars of every encounter with dark matter they have experienced over billions of years. one researcher described stellar streams as strings of pearls. And when you find a pearl necklace with a few scattered pearls nearby, you know something came along and broke the string. That something, in most cases, is dark matter, invisible, undetectable by direct means, but leaving its gravitational mark on the distribution of stars like footprints in cosmic sand. Among the primary scientific goals of the observatory is constraining the nature of dark energy through a technique called weak gravitational lensing, measuring the tiny distortions in the shapes of distant galaxies caused by the bending of light as it passes through the large-scale structure of the universe. This is extraordinarily delicate work. The distortions being measured are smaller than the apparent size of a human hair held at arm's length from your eye. To measure them with any statistical confidence, you need to observe billions of galaxies and track how their apparent shapes change over time. Only one instrument on Earth is capable of doing this at the required scale, and it is now operational. Here is what makes this scientifically explosive. In recent years, results from other major surveys, particularly the Dark Energy Spectroscopic Instrument, have hinted at something deeply uncomfortable. They have suggested, tentatively but persistently, that dark energy may not be a fixed constant of the universe. It may be evolving, changing over time. If that is true, it would mean that our foundational equations for how the universe expands, equations that underpin virtually all of modern cosmology, are incomplete. After a full year of data from the Rubin Observatory survey, its measurements are expected to reach a precision comparable to these recent dark energy results, providing a fully independent test of whether dark energy may be changing over time. This is not a routine calibration exercise. This is a direct confrontation with one of the most destabilizing ideas in contemporary physics. If Rubin confirms that dark energy is evolving, then the standard model of cosmology, our best working picture of the universe, will need to be fundamentally revised. And then there's the question that even the most cautious, most conservative astronomers will quietly admit keeps them up at night. Planetary scientist Mike Brown of Caltech, the same researcher whose work led to Pluto's reclassification, believes that the Rubin Observatory's survey data could finally resolve the mystery of Planet 9, a hypothesized world 5 to 10 times more massive than Earth that may be invisibly warping the orbits of distant objects in the outer solar system. Planet 9, if it exists, has never been directly observed. Its existence is inferred from the clustered, statistically improbable orbital behavior of a small group of trans-Neptunian objects, bodies in the cold outer reaches of our solar system, whose trajectories appear to be influenced by a massive, unseen gravitational presence. Most models suggest this hidden world orbits the Sun at a distance so vast that even at the speed of light, it would take months for a signal to reach it. It is out there if the models are right, moving through the deep darkness of interstellar space, patient, invisible, and enormous. The Rubin Observatory may find it, or it may find additional objects whose orbital patterns either strengthen or definitively kill the Planet 9 hypothesis. Even if Rubin cannot spot the planet directly, it could detect more objects with warped orbits pointing to Planet 9's existence, or alternatively, the absence of such objects would itself be an important result, a definitive nail in yet another planetary theory. Either way, within the next few years, humanity will have an answer to a question that has haunted astronomy for decades. And that answer, whatever it turns out to be, will permanently alter our picture of our own solar system. The Legacy Survey of Space and Time officially began in late June 2026, after a period of careful system optimization and a rigorous operational review covering image quality, survey speed, system reliability, and calibration accuracy. Each night, the observatory's camera captures thousands of images. Every few days, it completes a full scan of the entire southern sky. And throughout its decade-long mission, it will return to the same patches of sky hundreds of times, building not just a snapshot of the universe, but a motion picture of it, a living record of everything that changes, everything that moves, everything that appears for the first time, and everything that vanishes. In the first year of the Legacy Survey alone, Rubin is expected to capture images of more objects than all other optical observatories combined in the entirety of human history. That sentence deserves a moment of stillness. Every observatory ever built, every image ever taken through every telescope, from Galileo's first crude lens pointed at the moon to the Hubble Space Telescope's deepest exposures of the farthest reaches of the universe, the Rubin Observatory will exceed the cumulative total of all of that in its first 12 months of full operation. This is not incremental progress. This is a discontinuity, a before and after moment in the history of our species' relationship with the cosmos. When the full survey is complete, the final dataset will reveal asteroids and comets, pulsating stars, supernova explosions, the fossil record of galaxies, clues to the mysteries of dark energy and dark matter, and perhaps cosmic phenomena that no one has ever seen before, phenomena that may not even have names yet. That last part is the part that serious, credentialed, deeply conservative scientists keep coming back to. Because throughout the history of astronomy, every time a truly new kind of observational capability has come online, it has revealed something that nobody predicted. Radio telescopes revealed pulsars, neutron stars spinning hundreds of times per second and emitting beams of radio waves that nobody imagined could exist. X-ray observatories revealed black holes actively consuming neighboring stars. Gravitational wave detectors revealed the collision of black holes and neutron stars in events of incomprehensible violence. Every new way of looking at the universe has found something that rewrote the textbooks, and the Rubin Observatory is not a small incremental step forward. It is the largest leap in ground-based observational capability since the invention of the telescope itself. What most people are not seeing is that this is not simply a scientific instrument. The Vera Rubin Observatory represents a philosophical shift in how humanity understands its place in the cosmos. For centuries, looking at the sky meant pointing an instrument at a single target and learning about that one thing in extraordinary detail. The Rubin Observatory abolishes that paradigm entirely. When the LSST is complete, the final dataset will contain billions of objects with trillions of measurements, all accessible not just to professional scientists, but to anyone in the world who wants to engage with it and explore the dynamic universe in ways never before possible. This is the democratization of cosmic discovery. The universe, in unprecedented detail, made available to every human being on the planet who has the curiosity to look. The observatory is expected to provide data to help answer the question of Planet Nine's existence, and it will also produce an astronomical movie of the universe, the largest in history, through its time-lapse survey of the southern sky. But beyond the specific scientific targets, beyond dark matter and dark energy and Planet 9 and near-Earth asteroids, there's a deeper implication that informed sources within the astrophysics community are beginning to discuss with increasing seriousness. And that implication is this: we are almost certainly going to discover something that we do not have a theory for. Not a refinement of an existing theory, not a small anomaly that gets absorbed into existing models. Something genuinely, fundamentally new. The history of astronomy all but guarantees it. And with the Rubin Observatory now operational, generating data at a speed and scale that overwhelms every analytical framework we currently have, the window for that discovery may be shorter than anyone publicly acknowledges. The real story, the one that the mainstream science press has not yet fully grasped, is not about the images themselves. It is about the rate. It is about what happens to human understanding when the volume of new information exceeds our capacity to process it. Scientists around the world are already grappling with this. The 800,000 alerts from a single night in February, before the full survey even began, forced observatories globally to start developing new automated systems, new artificial intelligence pipelines, new protocols for deciding which cosmic events deserve immediate human attention and which can wait. 7 million alerts per night will demand infrastructure that does not yet fully exist. It will demand a new way of doing science, and perhaps that is the most quietly revolutionary thing about the Vera Rubin Observatory. It is not just changing what we know about the universe, it is changing how we learn about it. It is forcing the entire global scientific community to adapt, to build new tools, to think in new ways, to collaborate at scales that have never been attempted before. The universe has always been this vast, this dynamic, this overwhelming. We simply lacked the instrument capable of showing us the full picture. We have it now. So the question is no longer whether the Rubin Observatory will transform our understanding of the cosmos. It will. That is already certain. The question is what it will find that we are completely unprepared for. Because out there, in the data already captured and waiting to be analyzed, in the 60 million gigabytes of new sky that will accumulate every 3 nights for the next decade, something is waiting to be found. Something that was always there, hidden in plain sight, invisible to every instrument we ever built. Until now. Something that may be beautiful, something that may be terrifying, something that will force us to look at the universe and at ourselves in ways we have not yet imagined. The telescope is running. The data is flowing. And whatever is out there in the dark has nowhere left to hide.